Today's lecture is about sedimentary structures, and they are lots of features that you'll find in sedimentary rocks that are good clues to their depositional environment. And there are, I think, 13 of these that we're going to discuss, but I want you to know that there are whole courses taught on sedimentary structures. We're going to talk about several that you'll see in upcoming labs and assignments, and so definitely you want to take some good notes here because you'll be referring back to this, and I think you have a short assignment on it as well. So our first sedimentary structure is called graded bedding, and here you see a rock layer with a pen next to it for scale. And what I want to draw your attention to is the change in grain size here. Graded bedding is when you look at beds of sediment that the sizes of particles are sorted or graded, and that we can see here in this picture where particle sizes grades range from very coarse to medium to a little bit finer up towards the top of the bed right here. So that's called a fining upwards sequence when the particle size gets progressively finer as you move upward. A lot of time you'll see that abbreviated as FUS. So where might you find graded bedding? Well, graded bedding is something that would happen if there was a river that flooded. And so when the river first overcame its banks, it would be at flood stage, it would be moving very quickly. So the bigger the particle size, the higher the energy of the water that it was moving in. So when you initially have that flood surge, you'll have large particles that are deposited. As the flood begins to wane, though, the energy or the velocity of that river will start to decrease, and then it'll start to drop particles that are smaller and smaller until you get back to sort of your normal flow for a river where you might have medium or fine-grained sediment that's deposited. So another place you can see this is in something called a submarine landslide that geologists sometimes call turbidites. So I'm going to pull up a short clip here, and this is supposed to simulate a submarine landslide. It's basically a landslide that occurs underwater where you have sediment that's really saturated. This is called a sandbox model when geologists will make basically landscapes and then simulate events, and we can kind of observe in the modern what's happening and then use that to infer what happened in the past. So when you have this initial surge of sediment and the initial surge of water-saturated sediment down a slope like you would have underwater, the first thing that happens is the largest particles will get carried and then kind of deposited as the submarine landslide is moving down slope. This is really, really hard, as you might imagine, to capture on film. There are a couple examples where people have been caught in submarine landslides, but this is sort of the leading lobe of the landslide. And then as the biggest particles first settle, over time, the velocity of this landslide will decrease as the landslide ends. And so you'll have progressively finer material that then gets deposited. So this is one area, one situation, again, that's called a turbidite, where you can see graded bedding. Flooding is a second. A lot of times you'll have what are called parallel laminations in a rock layer. And what you might notice here, and here's an inch scale, bar scale here, is that the layering is parallel and really flat and really fine grained. Well, you see parallel laminations, again, this tells you about water energy, where you have really quiet water, really stagnant water. There's no ripples in this sediment. Everything is the same grain size. So what this tells you is that you have water where there is no or very low flow, where you have parallel laminations deposited. A lot of times you'll see these in shale, but you can certainly see these in sandstone and siltstones as well. So typically we end up talking about these sedimentary structures with clastic rocks, and that's typically true, but sometimes you'll see them in carbonate rocks as well, especially dolostone. All right, the third example of a sedimentary structure that you'll be seeing a bit of are called flute casts. And flute casts are always sort of characteristic because you have like these lobes and then they kind of splay out after you have sort of a nice tight nose on the lobe. So these actually, you're actually looking at the bottom of a bed here. This sample is completely flipped over. A lot of times in your lab on sedimentary structures, I will show you pictures with an arrow, and the arrow will indicate which direction is up, because this is actually the bottom of the bed. So flute casts are caused when sand fills into elongated depressions or long depressions in mud. And so what'll happen is a current will be flowing, and maybe there's like a pebble here at the top of each one of these little V-shaped divots, and the pebble is maybe too big for the water to carry, so the pebble sticks in the soil, in the sediment here, and the water will like refract around that pebble, and it will create like a little divot here. So here's the pebble, and then behind the pebble there'll be erosion, and maybe a second pebble here. Behind the pebble there'd be erosion, because there's a little, this is almost like a little eddy or a little whirlpool. Eddy is usually the word geologists use. Eddy is spelled E-D-D-Y, and it's just a more scientific term for a whirlpool. So then what happens is, after these divots are created, is very often this will happen in a shale, which is relatively weak, and then you'll have a siltstone or a sandstone that's deposited on top. And when that happens, that sandstone and siltstone are more resistant to weathering, and they will fill in all of these depressions here with sand. And then when you break the rock, those depressions are these lobes here. So in this particular sample, the current was moving kind of from the bottom left to the upper right as well. So good stuff. Those are flute casts, super characteristic. If you live in the Rochester area, there's lots of flute casts near like Stony Brook State Park, Grimes Glen, and I feel like there's one other one. But the Dansville area is, oh yeah, that was Stony Brook. Yeah, that might be it. Super characteristic, but pretty cool. All right. Also occurring along the bottom of the bed are tool marks. So here you can see there's a quarter for scale. In a lot of your labs this semester, you'll be spending time sketching, and it's really important in geology to include a scale in all of your sketches, because it helps the viewer and you know the size, the approximate size of what you're looking at. A lot of times you can see that you'll use a little bar scale, and sometimes you use an object that is of known size. So tool marks are these long depressions that are carved into the sediment below when water is dragging something along the bottom. So maybe there is a stick or a shell or something that is dragged along a muddy bottom, and that depression that it's created eventually will get filled up with a different type of sediment. Maybe it gets filled up with sand, and you have, when you see the word muddy bottom, muddy typically is connected with clay-sized particles. So really fine-grained particles that eventually, just like with the flute casts, get overlain by something a little bit larger in grain size, a little bit more resistant to weathering. Right, something else that also is typically found in shale is this sedimentary structure, which is called a lode structure. So here's a rock hammer for scale, and a rock hammer is probably about 15 inches in length, just for some idea. And so when you think about clay, when you think about mud, mud is actually somewhere between 85 to 90% water, which is why when you step in it, you sink down, because it's like stepping in water that just happens to be really thick. So a lode structure is created by something that is pushed and falls into or is deposited into mud. It forms when you have denser material, maybe it's a footprint even, or some heavier rock that's kind of sinks down and deforms the sediment below. So this would have been really muddy, really saturated with water, and then something squished down above it, and that created this lode structure. So that tells you that the environment that this was deposited in was water saturated for sure. Probably stagnant water. You can see that there's some parallel laminations in this section. You can see that wasn't always stagnant water, because some of the older chunks of this rock show some little ripple patterns, which we'll talk about shortly. So this is another picture of the Navajo sandstone. Oh, look, there's Professor Barone. All right, so we're in Zion National Park here. And this is called checkerboard mesa, and you can see why. So you can see these really large, this is a part of the Navajo sandstone that's been largely bleached out, where when it's at higher elevations, groundwater will come down through and kind of leach out the reddish portion of the sandstone, and it kind of leaches out the hematite, and it leaves the white quartz sandstone behind, or the quartz arenite, as it's sometimes called. So you can see these really large scale cross beds or cross stratification. And then the checkerboard comes from, these are called rills. Rills are just the very beginnings of rivers, and they kind of intersect to create this checkerboard pattern. So to me, there's fewer places that are awesome to see crossbeds than where the Navajo sandstone is exposed, and it's exposed nowhere better than Zion National Park. Here's a couple other pictures of some of the massive crossbeds in the Navajo sandstone in Zion National Park. This picture, I feel like I took, Barone and I were driving around Zion, it was getting close to the end of the afternoon, and there were like bighorn sheep that were coming down here with their young. It was so cool. But again, you can see some of the reddish stain here from hematite. And one of the things that you learned earlier this chapter is that this tells you this was deposited in a terrestrial environment, so on land. And this is, as I mentioned at the beginning of this chapter, these are petrified sand dunes, and the crossbeds are created by sand dunes and migration of sand dunes. They can also be caused at smaller scales in rivers. This is an animation that honestly used to be just available from the publisher and isn't anymore, but this is going to show you how those crossbeds are created. This is going to show you the wind pattern, and it's going to show you how sediment can be eroded from one side of a sand dune, carried by the wind, and then deposited sort of on the leeward side of that sand dune. So as wind direction changes, the orientation of the sand dune will also change. Thank you, Hassan. So anyway, crossbeds tell you that you are in a location that is characterized by sand dunes or wind, typically wind, transportation by wind. There's deposition along a slope. And while this is most common in sand dunes, it can also occur on a beach where you have sort of actually there's sand dunes on beaches. As you move up from the beach front, very often there'll be some really sweet sand dunes that help to actually hold the beach in place as a result of like wind and water erosion. So then finally, you can also have this sort of at the front of a delta, where a river meets a slower moving body of water, where that sediment is just deposited along the front of the delta. So that's fun. Crossbeds, pretty fun sedimentary structures as they go. All right, this is another example where you're looking at the bottom of a bed. So these are mud cracks, and some of the best mud cracks I've ever seen, quite honestly, were in a puddle in a Walmart parking lot, but they were perfect. This is another example of you looking at actually the bottom of the bed here. And this is a sledgehammer that is probably 2.5 feet in length or so. When you are looking at soft sedimentary rocks, rock hammers will typically work, but when you are looking at carbonate and denser material or sandier material, you need a sledgehammer to break those. So mud cracks are something that you've probably seen yourself. You've seen them, like I said, in Walmart parking lots where you have mud, and when that mud dries out, it cracks. So what that tells us is when we find this in a rock is that that rock was exposed to the air. The word we use for rocks being exposed to the air, or anything being exposed to the air, is subaerially exposed, which means beneath the air it is exposed and it dries out. So that typically tells you that you're in an area that is intermittently wet and dry, and that mud crack will get preserved when larger sediment gets deposited on top of the finer grained mud. So this is actually the infilling that fills in the mud cracks and preserves the shape of them. Good stuff. So these are harder to find, but these are called raindrop imprints. It's exactly what you do think. This is Professor Barrone's foot, and I believe that we are in Grand Escalante National Monument in Utah, driving around looking at stuff. And so you can see it's very dry in this area, and it had rained very recently. So you can have sometimes raindrops, especially in really dry places, the imprints form in mud. And very similar to the mud cracks, they can be filled in by overlying sediment that is maybe more resistant to weathering than the clay that you see here. Although you also see some larger particles as well, sand and some small gravel as well. So what this tells you is that the area here is also at least sometimes subaerially exposed. So again, exposed to land and exposed to air and not always water. So where do you find a region that is at least sometimes subaerially exposed? Well, this might be a floodplain, so the sides of a riverbank, right? Tidal flats. Tidal flats are really flat areas that when the tide comes in are covered with water, and when the tide goes out is subaerially exposed to the air, and then the tide will go in again and bury it. Lake shorelines, as we know in Rochester, the elevation of lakes can fluctuate greatly. So sometimes a lake bed or a lake shoreline might be exposed to air, and other times during a wetter season or during climate shifts, that area can then be sort of inundated with water. All right, there's just a few more. This is not always the most exciting of lectures, but you will make it through. And the next one is called wave ripples. So wave ripples are pretty fun. They are produced in areas that don't have a really strong current. And what will happen is that the waves kind of oscillate, sort of back and forth. They slosh back and forth. They are symmetrical waves. So what that means is that when you are looking at the waves, that there's not a distinct current, that this side of the wave is as steep as this side of the wave. The crests are typically pretty pointed. Very often with wave ripples, you'll find this Y-shaped pattern. And that, again, is characteristic of oscillatory waves. So that's exciting. So where this happens is in relatively shallow water and subaqueous setting. So that just means underwater. It doesn't necessarily mean submarine, because it's not in seawater necessarily. It's just underneath water. Good stuff. But sometimes you do have a distinct current, and that's when you create something called current ripples. Current ripples are when you have ripples that have asymmetrical crests. So when you actually touch them or when you look at them, you can see that one side of the crest or of the wave is more steeply dipping than the other. This is my old student Chris sitting on a fallen down slab of, I think, the Moenkopi Formation in Capitol Reef National Park. And we were just kind of climbing around and found this small sort of rock fall here, and you can see the ripple marks, the current ripples rather, and kind of infer from the steep direction where the water was flowing, which dominant direction for water flow you have. Oh, it's frozen. All fixed now. So yeah, the direction of the current ripples will tell you if there was a unidirectional flow of air in the case of sand dunes, or water in the case of shallow bodies of water that were probably either the water direction was driven by wind, or it could have also just been driven sort of by gravity as streams flow down slope. They're typically found in locations of high current velocity. So important for kind of reconstructing what past environments look like. And this is a black and white picture of some scalithos. So for scale, there is no scale in this picture. This is probably 2 to 3 inches across. And what these are vertical burrows through sand, and they're feeding burrows that are common in high energy environments that are close to the shoreline, where a lot of times you don't find full fossils in sedimentary rocks, but you will find these sort of sedimentary structures. And sometimes you don't find full fossils for a bunch of reasons. Either you have soft-bodied organisms that don't preserve well, or you have a lot of predation, or you have shells that are just broken up in waves. And so you very rarely will get, in some of those environments, like full unbroken fossils, but you'll often find evidence of life. And so here is an area where an organism sat and kind of schlepped its way down through the sediment, digging around, looking usually for food. Often attached to these vertical burrows, which again are called scolithos, are horizontal burrows, which are called arthrophycus. So this is the bottom of a bed, but it's really cool. So here you can imagine arthrophycus being connected to vertical burrows, where if this is the top, if you look at my cursor here, this is the seafloor, you can have organisms kind of, again, forming scolithos by digging around vertically and then finding some of that food, and maybe the organisms that they're feeding on or to the right here or to the left. And so that's how these horizontal burrows, which are called arthrophycus, end up being formed. They're often found connected to scolithos, and so they're also inferred to be feeding traces. All right, and finally, one of the most fun sedimentary structures to say is zoophycus. And zoophycus is also a feeding trace, but instead of it being sort of a vertical trace, it's a swirling pattern where an organism sat in this case, very stagnant moving water. You can see it's black, and you can see it's sort of fine grained, which is what you'd expect in slow moving water with not a lot of oxygen in it. And the organism would, in a fan-like way, kind of move around through the sediment, sifting for food. And then once it created the swirling pattern at this level, it would dig a little bit deeper and make another swirling pattern and deeper and deeper. So this is actually a three-dimensional sort of cone-shaped burrow, which is really cool, likely the feeding trace of worms. Zoophycus is historically found in siltstones and in shales, which are indicative of quiet water because it's very fine-grained sediment, where again water is stagnant or incredibly slow-moving. So these are your 13 sedimentary structures, and now let's practice applying some of those terms for a bit.